I'm making this video to accompany my application to an internship in Japan. The Okinawa Institute of Science and Technology studies things like, and I hope this brings to mind a certain talking squid, the mechanics of cognition by way of neurorobotics. I doubt the nice people reviewing my application will know quite what to make of a talking squid video. They probably won't even watch this. But I'm told the application process is extremely competitive. So, Professor Jun Tani, if you're listening, here's a project proposal. Jun Tani is the professor I'm applying under specifically. He's written a book I'd like to discuss titled Exploring Robotic Minds, examining consciousness from the perspectives of philosophy, biology, and his own experiments simulating minimal brains using recurrent neural networks. Professor Jun Tani quotes a lot of philosophers, but the first one is a big one. Aristotle said the mind is the part of the soul by which it knows and understands. That's not easy to translate into a robot's computer program. How does knowing and understanding become action and voice? Complex movements and statements can be broken into sequences of simpler parts, called primitives. So if we represent primitives with abstract symbols and make rules for combining them, maybe we're on our way to figuring out what it is we actually are. In fact, Edmund Husserl, phenomenologist, suggests turning direct experiences with the world into representations of it actually is consciousness. So how do we do that? Merleau-Ponty, discussing synesthesia, says our direct experience of the world is the result of our interactions with it. Likewise, Toru Tani provides the analogy of conscious experience being like describing a three-dimensional object using two-dimensional vocabulary, resolving ambiguities by understanding relationships between apparent contradictions. William James covers these and other observations in his 4 essential characteristics of the stream of consciousness. James said the stream of consciousness is totally subjective. The mind is all in your head. The stream is constantly changing, but only in a continuous way. And the stream of consciousness selects a part of itself to be the center of attention. So-called free will would be the ability to choose this center of attention and thereby choose our actions. We make choices by combining memories of the past with the present moment to generate possible sequences of primitives for the future and selecting from among them. If we've seen a situation 1,000 times before, we know just what to do because we've got habits learned from prior experience. If we ever don't know what to do, the conscious individual chooses a new action. The results of that action might establish a new habit in the future. This leads to stable perchings, where thoughts are predictable, and transitive flights, where thoughts are chaotic. Professor Jun Tani builds on these philosophical positions, proposing a circular causality as the defining trait of a mind at work. We've got a top-down perspective in which past experiences are projected onto the present to arrive at expectations for the future, but we also have a bottom-up perspective in which those expectations are compared with actual outcomes, and our mistakes adjust our further expectations. These two perspectives are constantly determining what it is we think we're trying to do. Tani cites an example from Martin Heidegger. An experienced carpenter hitting a nail with a hammer has deep muscle memories, ingrained sequences of primitives, which make the task automatic, as if the hammer is part of his hand. But if the carpenter misses the nail, suddenly the automatic process stops, and the hammer and hand are separated so the mistake can be evaluated and corrected. Professor Jun Tani writes a lot about the actual human brain, especially mirror neurons. Neurons stimulated when an action is performed or when another person is observed performing that action. Mirror neurons facilitate childhood development by enabling imitation of and communication with others. Brains discover patterns of primitives all around us. The front of our brain passes sequences of primitives to the more lizardy parts of our brain in the back to carry out and report back on. And although I think that's really interesting, I'm more of a math squid than a biology squid, so let's skip to that. Tani describes how dynamical systems are characterized by their attractors. A dynamical system has a state. A system's state determines the system's state at the next time step. An attractor is a pattern which states follow step by step as if caught by gravity. Maybe in a dynamical system, no matter how the state starts, it'll drift to the same state every time. Maybe states tend to swirl. Maybe something cool and fractally happens. Those are called chaotic or strange attractors, and they never repeat. They are aperiodic. Valentino Breitenberg, cyberneticist, proposed hypothetical little robot vehicles run by dynamical systems which react to their environment or even seem to have thoughts generated by chaotic attractors. In comparison to classical artificial intelligence, these Breitenberg vehicles would be simple, yet their behavior relatively more complex. Unlike a chess AI, the vehicle wouldn't be lost in a deep web of representations. The vehicle would react to quote-unquote direct experience of the world. Jun Tani took that idea and ran with it, actually building robots which interact with their environment and their experimenters, based on dynamical systems powered by recurrent neural networks. A regular old neural network is a feed-forward network. It can accept inputs and turn them into outputs using a big black box of linear algebra. We don't really know or care what happens inside the box, as long as it works well enough and quickly enough. But it doesn't start out working. The black box starts with random weights, and when it inevitably messes up, we tell the box it was wrong. The box uses our corrections to try better next time, by updating its weights with a technique called backpropagation. These simpler neural networks work surprisingly well for a whole bunch of tasks, but a recurrent neural network is more specialized. A recurrent neural network gets a context, like a memory, with its input, and its output includes updating the context. This makes recurrent neural networks helpful for natural language processing. A feed-forward network couldn't well predict the next word of a sentence because it doesn't have a notion of previous words. Recurrent neural networks can learn how past events impact the present, and they can imagine the future by closing their loop. Instead of performing the first action to come to mind, a robot could consider multiple actions in a row, predicting how the context would change with each one. Says Tani, this enables the robot to perform the mental simulation of arbitrary branching action sequences, as well as goal-directed planning to achieve given goal states. That sounds like William James's stream of consciousness. Actions are chosen by comparing the past with the present to choose a future. Tani's robots even feature the same stable perchings and transitive flights. When a robot correctly predicts how its actions will affect its context, the robot runs smoothly. That's the top-down path in action. When a robot's predictions are wrong, it devotes more time to hypothesizing about the future, leading to chaotic actions. That's the bottom-up path taking over until the top-down path can retake the controls. You'll notice there's no point where the robot makes a choice for itself. These periods of stability and chaos just emerge from the interaction between the robot and the world around it without what we meatbags might call authentic intent. Yet Jun Tani gives the example of his robots whose movements can be corrected manually. When you put your hands on the robots to show it what to do, you'll feel the robot resisting, like it has disagreeing desire. We feel intent in deterministic robots because we have limited awareness of how they work. We are some of those robots. June Tani says there's no room for free will anymore. Determinism has occupied the space. Yet we still feel like we have free will because our brains work so well. That's the tricky part. The goal here is kind of to annihilate the illusion of the self by understanding it well enough to make one. I've stalled enough to propose the project I'd like to work on at OIST. If my application is accepted, I'll do whatever they want. I'll fetch coffee if it means I get to look at neat robots. But I'd like to try making my own minimal brain to answer questions and raise more questions about what it is we actually are. I've never made a robot, but Tani seems okay with simulated robots, and I think that's more my speed. In particular, I'm inspired by the last pages of Exploring Robotic Minds, where Tani speculates about the potential for dynamical systems to generate emotional response and a theory of moral virtue. I want to make a dynamical system which interacts with us via stories. The system would be trained on dialogues between us experimenters as we tell stories and react to stories, using formalized language made of emojis, basically. The system should eventually be able to react to stories sensibly and tell us new stories which elicit specific reactions in us. I was hoping to show you some simple versions of this, but honestly, I've spent most of my free time lately just learning TensorFlow and natural language processing. So instead, here are some thought experiments to demonstrate how I think the storytelling system could work. The dynamical system is watching me use some hand puppets, tentacle puppets. This one's a clown and this one's a cowboy. The puppets represent emojis I'm using to tell a story. The clown is sad and says, "My elephant died." The cowboy becomes sad too. The dynamical system has no inherent emotional response to this series of emojis. It doesn't know what sadness is, and it doesn't know that a sad face represents sadness. It doesn't know what an elephant is, or what it means to die. Nevertheless, the pattern is remembered. Now the dynamical system is watching me use a puppet while it's got a puppet of its own. I've got a pirate, and it's got a robot appropriately. The dynamical system is constantly wondering what it should do with its puppet, or if the puppet should do anything at all. The pirate is sad and says, "My parrot died." The system remembers, "Hey, I once saw someone say something like that, and someone else made this face. That's a thing to do." If we gave it enough stories, it wouldn't matter that it doesn't know what these emojis mean to us. We could tell them all about our fictional pets, and it would nod along, or laugh, or cry, whatever was appropriate. To paraphrase Wittgenstein, the meaning of an emoji is its use in our text messages. More complex stories might teach the system moral virtues of right and wrong. Suppose the cowboy tells the clown his horse died, and the clown laughs. The cowboy becomes way more sad and calls the clown a butthead. Now, when the pirate tells the robot his parrot died, the robot might be sad, or it might laugh. If it does laugh, it'll remember that after someone laughs at something like that, someone gets sad and calls them a butthead. So if the pirate doesn't say it, maybe the robot will say it. It'd be like apologizing for its own rude behavior. We're obviously reading those emotions into it, but isn't that how mirror neurons work? Once the dynamical system is trained, it could be given puppets to play with. We could watch stories play out or join in with our own puppets. We could give puppets to external forces so the story reacts to the real world. If we don't like what the system does, we can admonish the offending puppets, or make them do something else, or take the puppets and make them move manually, so the system can learn from its mistakes and learn to tell stories consistent with how we see the world. Hopefully, the dynamical system would exhibit the same circularity as other models of the mind. Like any story, it starts in predictable, stable homeostasis. When disturbed, the story appears chaotic and unstable until it settles back around its attractors. Then we could, for example, teach the system to play Dungeons and Dragons with us, or host an improv comedy sketch with us. Those two things are more or less the same to what would theoretically be a generalized intelligence. I also imagine a sort of Turing test, where the system and isolated experimenters use puppets to tell one united story, and then experimenters independently guess which puppets were controlled by the robot. The robot's goal is for us humans to mistake its puppets for living people. Iterating this, maybe we could convince it to simulate free will in all kinds of ways. These ideas alone are interesting enough to me. A roboticist might need a little more. So what if the puppets represented physical mechanisms, and their emojis weren't emotions, but their instructions? Rotating left, rotating right, going up, going down. Physical robots could be piloted by stories, just like the story of the self animates our body. Whether my application is accepted or not, I'll keep thinking about this on my own. But I would love to think about this in Okinawa. So I hope this talking squid caught your interest, Professor. Bye-bye.